Okay, so what I'm going to do is I'm going to go back over the D algorithm, because the thing with the D algorithm, especially when it comes with the main test generation, justify and propagate with this. Okay, screen should be shared. Share. Present to everyone. There it is. All right, so I want to go back over 6.4, and then we're going to go back over this one as well, because I wanted you guys to get the idea of propagate and generate. So in this particular example, we have a generate test for a F stuck at 0 fault, right? So all of the algorithms in the write-up is a fancy way of saying, what do we do to generate the opposite of this value and then move on, right? So the whole idea, if it's a stuck at 0 fault, that means we want to be able to say, all right, if I put a 1 here, that should activate the error. And then whatever ends up coming through, and I need some sort of thing out here that I know that if I get some sort of input signals, the output will be wrong, and I know that this is a potential fault. So here we have a 1, right? So in order, the whole idea between justify is that we're trying to get these opposite values. So what we need is we would take the opposite of this 0 and we get a 1. And then what do I need on the gate here to get a 1, 1? To get a 1 on the output, they both have to be 1. Now, if this were an OR gate, that whole idea where we talk about either pick one or pick them all is that if I had a 1 on the output of the OR gate, then all I need is a 1 on one of them, right? So that way I can generate the error. So here I know that I need 1 and 1. So here I have a 1 here. So now I have to propagate this error. So what I have is I'm expecting a 1 and getting a 0, so I have D bar, right? So here I have to get D bar to this output. I have to have a situation where I'm expecting 1 on this output and getting a 0. So if G is equal to 1, so that means we know the controlling value, right? The controlling value is a 1. An OR, which means if I put a 1 on the output, on the input of an OR gate, it will put a 1 on the output. So if I want D bar on this output, like so, then I have to have the opposite of the controlling value, which means this is 0. So that has to be a 0. So then justify, we go backwards. Well, in order to get a 0 on here, I either need, since 0 is the controlling value of x, it either needs to be 0 or x or 0, right? So it can be one or the other. So therefore, we know that A has to be 1, B has to be 1. We can say 0 and x, right? So we have D bar here. So now I need to get D bar onto the output of J. So what is the controlling value of an AND gate? 1, that is incorrect, it is 0. 0. The controlling value means that if I put a value on any of the inputs, it controls the output, right? So that means that if it's a 0, that means it'll automatically propagate a 0 to the output. If I put a 1, then it's the other values. So for example, if I have a 1 here on A, then whatever the value of B is, it's going to be propagated. It doesn't control it. So here, if I want D bar on the output, I don't want this line controlling it. Does that make sense? So then what I have to do is I got to put a 1 here. So then it goes back. I have to invert it, so E becomes 0, and that becomes our input signal, right? Does that make sense how I did that? So I included the whole algorithm, and this is the whole thing, where basically what I just showed you is this chart here. So then here we've got the error reach the primary output. And so as we set up here, that's the input, 1, 1, 0, x, 0. And so the whole idea behind the D algorithm is that we have the situation where we have fan out. Now fan out has a problem, and so we have this situation here where I describe a stuck at 1 fault with fan out. Fan out 1, so we need 0 here on the input, right? So I'm expecting a 1, I'm expecting a 0 and getting a 1. So what happens is in order to get 0 on the input of a NAND gate, I need all 3 inputs to be 1. So that puts a 1 here, right, on the input of the NOR. So what ends up happening is that we have, no matter what D is, if I put a 1 on the gate of a NOR, I'm going to get a 0 on the output, right? And since a 0 is the controlling signal for an AND, I will get a 0 on the output here. Likewise, if I put a 1 here, I'm going to get a 0, so it's going to invert. So I get a 0 on this OR gate. This is NOR gate. So that means since 0 is not the controlling value of the OR gate, it's just going to propagate E, right? And so E is going to come here, right? So since I have D bar, I'm expecting a 0 and getting a 1. That puts a 1 here. And since a 1 is not the controlling value of an AND gate, that means that the output of F2 is controlled by the other input, which we know to be E. Which means that E is the value on the output, not the error. Likewise up here, 0 is the controlling value of the AND gate. That means that 0 controls the output, not the error. That means that in this situation, we have not propagated the error to the output using those 3 input control signals. So what we have to do is that we have to use this D algorithm in order to figure out how to propagate the signals when we get this initial error here. And so what happens is instead of just going a sad face, we'll never find it. What we're going to want to do is we want to backtrack. That's the whole idea behind backtracking. Let me move on from there. And then this paragraph basically just says what I just said. And here I'm describing a situation where we don't have fan out, but we're generating a signal here. So we want to propagate the value to the output, right? And here what we're showing is that we have multiple signals. Basically figured out the whole set of the particular fault with 3 signals, even though there's a potential of 16. So by reducing that, we can actually come up with the minimum number of faults. So advanced test pattern generation, ATPG, is what we're doing here. So basically what we're doing is, okay, so this little algorithm here, and there's a reason I don't have it as a TGO. Basically what you would do is you'd go through the entire circuit and pick each node and do stuck at 0, stuck at 1, and go through and then add them to a set of output signals. And if the output signal is already contained, then you just don't do that. So therefore, you know that if you run this minimum 1 and you're expecting certain values and one of them comes out wrong, you know that you have some fault. And so this backtracking algorithm, we search for a test vector and we do a decision process, and we talked about these D frontier and Q frontiers. And if it leads to an inconsistency, then we backtrack, meaning that we're expecting a specific value, but if the fan out causes a different value, then we go back to what value that caused that, we change it, and then we move on. So we have a systematic exploration and recover from incorrect decisions. We discussed these concepts of the D frontier, J frontier, and unique D drives. And then we have the 3 steps of the implication process for that D algorithm. We compute all the values that can be uniquely determined by the implication, and we saw that as I went through the whole circuit. Check for consistency in assigned values, and then maintain the D frontier and J frontier. And then I went over the actual D algorithm, and then I have a situation where I described this circuit in example 3.5. So first I have a stuck at 1 fault, right, on the input A, but it's after this node. So I want to put the opposite value. So it's kind of the same concept, we're inverting. So I have the value of A is 0, right? So that means this value, 0, goes all the way up to this NAND gate. And here. So we're here, we have a 0, we're expecting a 1, so that becomes D bar. Now, if you recall, we need to propagate this value to the output, which means we don't want, which means the purpose of these two inputs means it has to put it through. Now, if you consider an AND or an OR, if you have a 0 on B or C, then what ends up happening is those values automatically get propagated. It doesn't matter what's on that wire. So we know, based on, and this is why I have this here, we know B and C must be 1 to propagate D to G. Here we have D, we have D bar, right? And it goes 1, 1. And if we're expecting a 0 and we get a 1 here, then on the output we're expecting it. We got a value of D here. We're expecting 1, getting a 0, right? So it's 1, 1, 1. So if we're getting 1, 1, 0, we're expecting a 1 on the output, right? But we get a 1 instead, so we get a 0. So we get D on the output. So we start out with D bar here, and we got D here. Does that make sense? So we know that B and C must be 1. And that A must be 0. So we have our 3 inputs. So that means that 0 ends up here, B, 1 ends up there, and C, we follow this far into G5, then we get 1 there. Does that make sense? So we now know that we've put G1, G3, and G5, and then we have these values up on G7. Right? Therefore, we also know that G1, because 0 is a controlling value on a NAND gate, we know that H must be 1 because it's a NAND. And if 1's at here, that means we have put a value on G7, right? That means our J frontier contains G1, G3, G5, and G7. And G here has D on there. And we've put D on G2, G4, and G6. So you see the difference there? That's why the D frontier is G2, G4, and G6. Okay, so now that we know that H is 1, right, and A is 0, we have to, what do we have to do to propagate this value here, right? So if we have D is 0, right, or D bar is 0, and we pick D is equal to 1, right? Well, hold on. That's going to be fine. If we pick, the key thing is we have D coming here up to G2, right? So we want to get, if we had a 1, we're expecting a 1 and getting a 0, then using NAND, we want to propagate that and get D bar on this output, right? So what I need is I need a 1 here to ensure that happens. And that means, no, it's D here, and with the NAND gate, if you see, so if it's D and 1 on a NAND, it's going to produce D bar on the output. Because here we're expecting a 1 and getting a 0, and here we're expecting a 0 and getting a 1. Because 1 and 0 will put a 1 on the output of the NAND gate. Does that make sense? Okay, good. Okay, so we have D bar goes here. This takes G1 out of the, so now that we've propagated the value to the output, this takes G1 out of the J frontier and makes I equal to D bar. And so now we have I and D bar here. So now this takes G7 out and puts it in the D frontier. Does that make sense? Right, so now we have to figure out how to continue to get this D bar error propagated. So here, what ends up happening is, well, I need to consider what values of J are coming out here, right? So I have E, this value E, and E bar, and 1 here, right? So 1 is not a controlling value, right? So what I don't want is if I have a 1 and a 1, I'll get a 0 on the output of this NAND gate. And a 0, if I get a 0 on this output here, it will automatically drive G7. Does that make sense? So what I want is I want a 1 here. So in order to do that, I have to have f equal to 0. I have to have e bar equal to 0. Therefore, e has to be equal to 1. That puts 1 here on G4. So I'll make e equal to 1. And so therefore we have D comes up through here. I'm sorry, yeah, D and 1, we'll put D bar there. So I have 1 D bar, 1 and D bar. So here they're still propagating through. And so I'm changing the colors by steps. Okay. So we also have G5 here, right? So G5, I have a 1 on this input from C, correct? That also means that I can't propagate a 0 here because that'll then control G7, right? So that means I have to have a 1 here. So I have 1 and 1. I need a 0 here. Does that make sense? Need a 0, and F bar, push it to F, that brings it to 1. I have a 1 here. I have G6, well then D is here as well. That's D, not D bar, sorry. So 1 in D is going to put D bar on this output. So with several inputs there, if they're all 1s, and then what ends up happening with D bar is I have 1 D bar, 1 D bar, 1 and D bar on the inputs, right? That means I'm expecting a 0 and getting a 1, so it's 1 0 1 0. In this case, I should get a 1 on the output, but I'm going to get a 0 instead, which means I've propagated D to the output. Did it again. Make sense? So that's how we end up doing the algorithm there, that we go through, we propagate, and then we backtrack and propagate and backtrack and propagate and backtrack. Okay? And these contradictions are fine. There. And so as we came up with, the test vector is 0, and then all the rest were 1s. Okay, so does that make sense? So why don't we make this, we'll do everything the same here, except this is going to be stuck at 0 fault. So let's work through it that way. So if it's stuck at 0, that means I want to have A equal 1 in order to propagate it. So that means I'm going to have 0 here. That means I'm going to have 0 here. I'm sorry, I'm going to have 1 here, right? From there. So if I have 0, I can just basically then pick what values I want to propagate. And this is where evaluating the contradiction becomes really important, right? Okay. No, I got it, guys. I saw what you guys are doing. Hey, relax. I'm allowed to make mistakes every once in a while. All right, so 1 goes here. Right there, right? So then the value of D bar is going to be propagated through here. I do not want 0 here. Does that make sense? If I don't get 0 there, then it's automatically going to control it, and I cannot do that. So if I have a 1 there, that means I need to ensure that I get a 1 on this output, right? So that would be a contradiction. So therefore, if I have 1 and 1 here, what I need, if I put 1 and 1 on the output, it would be a 0. So I need a 0 here, and that becomes a 1, right? So it puts a 1 there. So if I get 1 here, and I get a 0 here, then what I would need is a situation where that value gets propagated. So if I put a 0, if I get a 1 there, it doesn't really matter what the other inputs would be there, right? So here I would just have a 1, 1, because I want this one to drive it. So we have 1, 1, 1 on those inputs. Does that make sense? So here I am expecting, I have 1, 1, 0, so I'm expecting 1. And then, but I'm getting a 0 on the output. I'm sorry, this is stuck at 0. Okay, so it's stuck at 0. So what I'm expecting, 1, 1, 1, I'm expecting 0, but I'm getting a 1. So I'm getting a D bar here. So I get D bar here, I get 1, that becomes D. Likewise, B comes here, I have to put 1 there. So and C is put in G5. See how that works? So then what ends up happening is I have 1 here and I want to propagate a 1 here on the output since I don't have an error on the inputs, any of the inputs. So I have to have E bar equals 0, therefore E equals 1. That puts 1 there, puts D bar here, and gives me D, right? From there I have, this is what I have 1 from C. I want a 1 here, so that way it's not controlling the output. F bar then must be 0, that means F must be 1. It puts 1 here, I get D bar there, and that puts D here. So that means all 1s would do the stuck at 0 fall. Okay. Does that make sense? Cool. Let's see. Nah, I think you guys understand it. So if you wanted to practice, I would say just pick random nodes and say stuck at 1 or stuck at 0. Because what's going to end up happening is if you have a stuck at 1 fault here, that means I want this one to be a 0. It's going to put a 1 there, right? So I want to propagate the error. So this would be, I'm expecting a, I would expect a 1, but I'm getting a 0, right? So I get D. I want to propagate D out here. So that means I have to have 1 there, and that puts it at A is 1. Okay? So therefore, if I get 0, right? 0 is going to put a 1 there. But I want to make sure I have a 1 there. So this doesn't really matter, right? So G here doesn't really matter because I know what I get. So then I can go here. D3, I have a, up here I have a value of A is, I'm sorry, B. What I want here is a 1 on the output because I don't want it driving. See, all the rest of these aren't affected by the error. So what I would do is I'd say all these should be 1. So I have to figure out what it could be. So in that case, if I have a 1 on the output, then if I put a 1 here, that makes E equals 0. Right? So then I don't even care what B is, because also I don't care what this is. Same thing, goes here, 0, puts a 1 on the output automatically. I'm sorry, hold on. If I want a 1 on the output there, put a 0 there on the input, that makes E equal 1, E equals 1 here. And so then I want to come up with some sort of combination here that'll give me a 0. So here I know that A is 1, B, if I just say that's 1, and C is equal to 1, that'll give me a 0 here. And then this puts a 0 here as well, which will give me a 1 on that gate. C is going to be 1. So I want a 1 on there. So I want F bar to be 0. That's going to be 1. Right? So this has the 0 coming here. That'll control it. And that gives me the values there. So I know 1, 1, 1, 0, 1, 1. We'll find that stuck at 1 fault. Does that make sense? Cool. All right. So does D algorithm make a lot more sense? Good. Yeah, that's graduate level stuff there that I'm adding here. This is something I learned in grad school, so you are way ahead of the game. So what I want to do in the last portions of section 6 here is start talking about other ways that we incorporate testing and into the design of circuits. When we get into Virtuoso and skill programming, you're going to learn about these concepts of boundary scanning and scan registers and how we actually use these to actually use flip-flops to go around so that way it's constantly testing the circuit. So what we're going to talk about here is this first concept of boundary scans. So the name kind of makes sense when you think about it. Boundary scans. I want to scan at the boundary. Right? If I want to protect a house, well, the best thing I can do is test all the doors. And if somebody tries entering the doors or the windows, then I know it's a very good sign that someone or something is in the house that shouldn't be. Right? There's no need to explicitly check under every table or under every door until one of the doors or windows has been violated. Then you need to go, okay, well, if that's broken, then I need to go inside the house and see if I can find an intruder, or if it's some sort of bird that's going in, causing all kinds of whatever, right? There could be all kinds of reasons why your boundary has been violated. Well, in the same kind of way, we use boundary scan concepts in circuits. So the whole thing here is, I'm just going to turn my phone off. This is obnoxious. And it's people who I told that I have lecture at 1 should know better, right? In the signs of scan, the registers, so we have registers around the boundary to monitor this current state. The registers operate in one of two modes. In normal mode, they behave as expected, so they're just propagating everything through. But if we have this scan mode, they are connected to form a giant shift register or scan chain spanning the entire chip. By applying n clock pulses in scan mode, all n bits of the state of the system can be shifted out and a new set of n bits can be shifted in. Therefore, scan mode gives easy observability and controllability of every register in the system. So I come up with a set of inputs that I want to run, and then I run scan mode. So then what ends up happening is that in scan mode, the boundary scan registers will collect these values that I want. And so let's say I'm trying to test an ALU, and I put in different set of inputs, and it gives me an output. And then I tie the output of the ALU to the boundary scan. So the boundary scan says, all right, well, in this specific thing, I do this specific operation. Think about the MIPS data path, right? So in this specific operation, what I would do is I would run let's just do single cycle for simplicity's sake. No, well, actually, you do 5 cycles and then collect everything on the boundary scan with that cycle. So I run a command, an add command, and then I run 5 cycles. I know what comes out, what comes out of the instruction memory. I can collect those in the boundary scan. I then have an instruction decoder, so I get my opcode, everything that's going into the registers, score those in the boundary scan, and then cycle 3, it would be obtained in from the output of the arithmetic logic unit, the output of both registers, and then I have what's going to the data memory in cycle 4, and then cycle 5 I have what's written back to the registers. So if I collect all of these and I run it and I'm expecting a specific value on the boundary scan, I should know specifically what everything is based on this test instruction. And so what ends up happening is if I get a specific value, I test them all and I get, I'd say I have 256 outputs I'm measuring. And 255 of them are right, but like everything's right, and then things start suddenly going wrong. Then I can pretty much break it in half using the troubleshooting method I taught you guys and go, okay, so let's cut this, and everything over here on this side is right. So now I know that I'm getting wrong values in the ALU. I know I'm getting wrong values as being sent to data memory. I know I'm getting wrong values getting read back to the register. So what I would test is, all right, so I would test the input and the output of stage 3. And then suddenly I would say, okay, well, there's my error. And then I would try to troubleshoot where the ALU would be, and eventually I'd find out there's some sort of fault stuck at 0 fault in my arithmetic logic unit that was causing mistakes in adding. Make sense? So that's a good way of how I would use scan mode here for easy observability and controllability of every register in the system. So formally defined, boundary scan is a method for testing interconnects, wire lines, on printed circuit boards or subblocks inside an integrated circuit. So in designing modes such as complex chips or process control boards for testing and fault isolation, we should be able to isolate one module for another, and that's kind of what I was just describing there in the idea of MIPS. So all chips on board are designed using boundary scan architectures. So specifically on the outside, I was talking about what we would be collecting, and we'd be collecting them in these scan registers. Specifically, scan registers are flip-flops used to provide scan design capabilities. When the scan signal is deasserted, right, means it's 0, the register behaves as a conventional device. So that means we have our conventional signal going through, and then it's propagated. Obviously, a flip-flop is normal. When it's asserted, meaning scan is now 1, now I'm doing this value. When scan is asserted, the data is loaded from the SI pin, which is connected in shift register fashion to the previous Q register in the scan chain. So what I'm doing is I have, through the boundary scan, I have a specific set of data that I want to run when I do the test. And what ends up happening is I did a scan chain, and then it brings in the data from the stored values, puts it through, and then runs the test on the circuit. And a lot of times so routinely test them in order to ensure that they're working correctly regularly. So you can one of the benefits of this is that, okay, let's say I have developed a perfect circuit and I send it out to the user. And the user gets it and tests it and runs all the tests, and provides 100% coverage or very, very close to 100% coverage, and it works. Well, that's working now. But what ends up happening if after a certain amount of time I get an error? It's not working anymore. Well, customer's not going to be super happy because now suddenly their computer chip doesn't work. And you guys, if you've ever dealt with customers before, you're working at Kroger or anywhere with a customer service, and they're coming straight out of Easter service and they've heard about forgiveness and love, and then they berate somebody for not ringing up the Doritos correctly. Customers are not exactly the most rational human beings. But what you can do is you can take the data from regular boundary scan, catch it immediately, and you get that data back as a company. Well, why is that beneficial to you? If you get this, and you get this from one person, and so let's say, I am the company and you are all my customers, right? And right around the same time, I suddenly get a message from Samuel, I get a message from Andrew, I get a message from Zachary, I get a message from Therese, I get a message from Alex and Maisha, and they're all telling me that suddenly they're getting weird issues. And so I collect all my boundary scan data and go, oh, we seem to, because of the way we haven't laid it out properly, or we did something else we didn't anticipate, we are overusing a specific portion of the IC, and as a result, we're developing some sort of fault. Right? For example, we talked about when you go to Foundry, and we talked in section 5 about how you have pins and you don't design it properly, so they end up disconnecting or fusing or the different layers. As a result, you'll get really minor errors. But if you can notice that in advance, you can immediately account for that in future designs, and so you don't end up having to do multi-million-dollar or almost billion-dollar recalls like Intel did. So these are beneficial for you long term. Okay. So, as I've alluded to, scan registers are on the periphery. They are not part of the function itself. So you're adding that on top of it. So see, none of you took I think Alex, you took my low power course, right? With Genus and everything. So with Genus, you added boundary scanning and design for test after you design the circuit. So basically what you do is you come up with an area, and then you add all these things to it, and there's actual algorithms that are done at those levels, so that way they can actually test all of your outputs. And part of that is coming up with a minimum set that we need to test in order to ensure the circuit works. And you got a taste of that in this course by understanding how the D algorithm works. And so what's going on here is that I have my logic cloud. So this could be instruction decode, and this could be execute, right? And then all the outputs that I want to test have normal flip-flops. So I'm sending these values to the output as normal, but then I run this, I assert the boundary scan signal, and then I take that allows me to propagate values from data. Now, one thing that I did when I was an undergraduate and I was taking CMOS VLSI, we designed a digital thermometer. And as part of it, and in fact, I could probably dig up my final design and design report and email it to you. To this day, it's still the smallest design that they've had in any of those classes. But one of the things was we had to do boundary scan. So somebody comes up, they push a button, and instead of doing the normal temperature measurement that it was doing, it's getting an 8-bit temperature measurement from a sensor, it then picks a set of values and runs them and should actually come up with a specific output. Okay, so with the idea, and those of you who have taken 386, you understand that, you ever had to deal with a situation where the board wasn't working quite right? Yes, everybody. Testing boards is also difficult. So it's not just that you have to do that. You have to verify that the solder joints are good, so you can drive a pin from 0 and then to 1, right? So we have controllability and readability of the circuits. And the reason I mention this is because these boards also have a lot of boundary scans and design for tests. So that way you can figure out what part of the board is not working. So maybe you have to get rid of the Vertex 5 chip, or you have to add, replace a certain portion. That way, the moment you're not getting the correct values, you don't just go, okay, well, I'm going to throw away this, $1,000 board. I'm going to just perform minor troubleshooting, solder it back in there, and it's working again. And so this is another example of how the boundary scan works. Chips with internal scan chains can access the chains through boundary scan for a unified test strategy. So the unified test strategy is kind of what I was just describing. You have this whole goal where you have multiple chips. So if you are working on, if you have a quad-core processor, you can connect the entire boundary scan chain to each core and do all the testing that way. That way you don't have to worry about fan in and fan out on the boundary scans. Okay, so as part of this, we are going to try this concept of built-in self-test. So now you're starting to recognize all the acronyms that I have in the syllabus that I said I would cover towards the end of the regular lecture portion. So we have advanced test pattern generation, we have boundary scans, and now we have this built-in self-test, which is often referred to as online or offline BIST. And so it's defined formally as the capability of a circuit in your chip board or system to test itself, right? So think of it this way, built-in, if you are preparing for an exam, next week possibly, how would you actually prepare yourself? You develop problems and try to think of questions and study terms, right? So what you want to do is you're eventually learning over time how to test your own knowledge of a subject. Well, it's the same kind of concept here. How does a chip actually test itself when it's under duress, when it's being used out in the field, outside of controlled laboratory environments? And so we define them between online and offline BIST. So online BIST is when the testing occurs during the normal function. So we have the circuit's normally operating, and then we're just in real time operating, determining if the circuit is working. And then offline BIST is what happens when we shut the circuit down and then we run a boundary scan or other kinds of built-in self-tests. And so this question, example 6.6, comes straight from the textbook. And so I wanted to go over the solution with you about the principles and what are the advantages and disadvantages of BIST to give you an idea of why this is used. So first we say that BIST builds on boundary scanning by surrounding logic blocks with a pseudo-random sequence generator on the logic inputs and a scan chain on the output of the logic. So I have some sort of pseudo-random number generator. It generates a set of inputs just randomly, right? And then based on that set of inputs, I am expecting a certain set of outputs. So here, the benefit is that these two functions, in addition to the normal operation of the flip-flops on the scan, may be combined into the one structure. This allows built-in self-test to reduce the number of external test vectors needed if it is compatible with the system test methodology. So if I'm doing it pseudo-randomly, and I know what the output could be, I can actually reduce the number of outputs. However, I can also perform high-speed testing with a low-speed tester. But the main drawback is it costs area. So you have to add silicon, which costs money. Okay, so this is for those of you who are super geeks like me. You'll be happy to know that the built-in logic block observer for BIST is known as Bilbo. And so the whole idea is that it has two control signals. So Bilbo has normal boundary scan performed when these values here, right, are C0 and C1. So I combine this whole thing here. And so Bilbo has 4 different operations. And when I'm just doing 0, 0, what ends up happening is 0 on an AND gate, 0 on an AND gate, 0 on an AND gate, right? That means nothing goes through. So that means I just have I got 0 here. That gives me the normal operation on the output, right? So when I do 0, 1, we're going to actually perform the built-in self-test. So again, but here we have 1. So now we have our sequential self-testing. Does that make sense? So if I do 1, 0, I have this regular operation here, but I'm also propagating these values here, right? And so this allows me to reset the flip-flops. And if it's 1, 1, well then I get the value here. And then based on these operations, I can control the flip-flops, which means it's a normal operation. So the TGO includes both the flip-flop combination and the truth table. So does that make sense? So the whole idea is we're using these all around the circuit to then say, all right, normally I want it 1, 1, I want it operating. And I can use that to monitor if the circuit should work. But if I want to do built-in self-test or boundary scans, I could actually do that. If I want to reset the flip-flops to start normal operation again, I do 1, 0, and I go back to 1, 1. So the way it would work, it starts out at 1, 1, and then what I want to do is I say, okay, well I want to perform built-in self-test. I do 0, 1. It performs the entire built-in self-test. And then from the operating system, I say, all right, well I need 1, 0. I need to reset the flip-flops. And if you recall from error testing, you would have a set of backed up registered values from the error registers. It tells you everything is. You bring it back in using the operating system, and then you go to 1, 1 again. And as part of that command, if you remember from the instruction memory where it goes back to run the error program counter, that go back there, and as part of it, it will reset 1, 1 normal operation on the boundary scan. Okay, so does that make sense? Okay. What I'm going to do is I am going to, okay, so I'm going to dismiss you guys now because that's a logical place to end, and we got like 3 minutes anyway. What we're going to talk about next lecture is this idea of robustness. And throughout lecture, I've alluded a lot to these concepts of process variations, process corners, how everything's laid out in the circuit, and how that can be complicated. So what I want to go over here is this idea of process variations, how you can test for them in design, and we're going to go into a lot of shmoo plots. So what I'm going to do is I'm going to go over this on Friday. We will probably conclude section 6. And then what I'm going to do is I'm going to allow you guys to have the 2 days again, like I did before, to go over, review, ask questions. And then next Friday will be your second exam. That'll be the last exam in the course. Everything from then on out will be projects. So you'll be continuing. You'll be working. You all took my cadence courses. Unfortunately, Maisha and well, Alex, you did too, but Maisha and George came along a little earlier before I was able to get that out of cadence. We're going to have 2 separate courses. It's going to be Virtuoso Layout Design Basics. You're actually going to learn how to use your Lambda design rules to actually lay out circuits, and you're going to design a really nice circuit. And then what you're going to do is you're going to learn a programming language called Skill, which is going to allow you to actually write up code that will lay out the circuit for you. And so then from there, I think you would be very strong CMOS VLSI designers. So does anybody have any questions before I shut down lecture? Excellent. You guys are coming on very well.